Okay. I set up beginnings of the graph here. I'm going to draw the fundamental rectangle. I've got the lines where x equals 2, -2, and x equals 2. Got the line y equals 4. So I'll be able to locate my corner points. And sketching pretty good work. Okay. So this distance ought to be this distance, a little high, but not too bad. Okay. And I can also sketch my x-squared parabola. Okay, if I come down to here, there's 2, come down to here, there's 1, and I'm going to kind of. Here. I've told you that this parabola, and shown that, you know, plausibly this parabola represents y equals x squared. If y equals x squared, then -1 squared being equal to 1 and 1 squared equal to 1. We get these 2 points, and of course we know we have this point, and this point. Now you don't have to know these points right now. We're going to go in detail on the construction of a parabola. But if you want to store that away, it's fine. We're trying to get a good parabola. This power goes up a little too slow. So I turn around a little too quick here. I'll never learn. But there we have our x-squared parabola, and everything there just follows immediately from things we did previously. Okay. Now what I'm going to do is I'm going to double the height of this square. So it's no longer a square, obviously. I've drawn the vertical line slightly outside the square, so it's not perfect. But we understand what we're getting at here. Okay, yeah, this line isn't perfectly vertical. Looks a little better when I get over here. This one's kind of heading in toward the y-axis a little bit. So it's not great, but so what I've essentially done is I've stretched out this square to make a rectangle of the same width but twice as high. That's not too bad. Okay. Well, I can do that, and then I can sketch my parabola. If I sketch the parabola correctly, and we'll kind of test that. There's a way to test, a couple of ways to test it. I don't want to go too far into the other. Okay, so far so good. Okay, that's not too bad. So in stretching out this square, I've stretched out the entire parabola. Imagine we have a flexible sheet of some material that's stretching. Then we sketch this red line, or this red parabola, and then we stretch it out twice as far, and we get, well, the red parabola would then go where the yellow parabola is. We'd end up with a yellow parabola. Okay. So, fairly simple idea. You can simply double the height. And we say that I've vertically stretched we'll call this vertically stretched I'm going to use FS, the fundamental square. I've used that before, didn't mention it. And it's vertically stretched by a factor of 2. So that the yellow parabola is what I'm going to call the fundamental parabola. So I've got to do some abbreviation because it'd leave myself a lot of room here. But I'm going to call this the fundamental parabola, vertically stretched by factor 2. There it is. Now I'm going to claim now. Well, we'll talk about what the formula for this one ought to be. But let's see, just for the heck of it, how well did I draw this? If I draw a vertical line through x equals 1, and it looks like the vertical line intersects the yellow parabola here and the red parabola here. Now that's actually a little bit to the right of x equals 1. It's a good thing because these things are a little fine. Okay. Now, if I draw an arrow here to here, and then draw another arrow of the same length, I end up on the yellow parabola. Specifically, I draw an arrow from the x-axis up to this point, the vertical arrow, and another vertical arrow of the same length is going to land on the yellow parabola because the yellow parabola has been stretched out by a factor of 2. If I do the same thing, let's say over here, this is probably not going to work out as nicely, but let's just see what happens. I don't know what this x coordinate is. It looks like I am the red parabola here and the yellow parabola here. So now we've got a vector here, an arrow. This arrow and this arrow should theoretically be of the same length, and they're pretty close. This one is a little longer than this one. In other words, from this point up to this point is a little longer than from this one to this one. So this is a little more than double this. But of course, this is a hand sketch graph, and they're close enough to doubling. And it should be obvious that they really ought to be doubled. This thing has really been stretched the way I say it has. One thing I want you to see is that these arrows are shorter than these arrows. So if I move from this graph up to this graph, I've got to move further over here than I do over here. Should be obvious that the further I am from the x-axis, the further I'm going to have to move if I'm doubling my distance. Okay, so there it is. Now I'll say one more thing about this. The formula for the red one is y equals x squared. The formula for the yellow parabola is, can you guess what it would be? Take a minute to think about it. What do you think the formula for this yellow parabola would be? Well, hopefully you've got an idea, but if not, let me give you another little bit. And again, pause and ponder each question. How do the y values on the yellow parabola for given x compare to the x values? Well, hopefully you've thought about that. I'm going to give it away now. They're twice as great. The y values here appear to always be twice as great as these, and they certainly should if I stretch this thing out uniformly. So if this is y equals x squared, this has to be y equals 2x squared. So there's a graph of y equals 2x squared. Now, if I want to move that graph, let's say 3 units to the right and 6 units up, moving 3 units to the right, I'd replace x by x minus 3, and then it adds 6 on the end. Now, we'll put all that together. But right there, you have quite a bit of the idea of how we manipulate parabolas, how we can begin to analyze parabolas. Now, the analysis gets somewhat algebraic, but the picture is just the picture I've shown you. And if you have the picture, then the algebra is going to make a lot more sense. And incidentally, I've been going on with this. I do apologize for the fact that you can't see my top of my head, but it's the way the boards need to be. It's where they need to be, and that's where the camera needs to go. It's right there's the top of my head. Okay. These pictures are central to truly understanding what we do when we analyze functions. Now, that's something we're going to spend a month beginning to learn to do. In about a month, we'll have a complete theory of parabolas. And there'll be a fair amount of algebra, but if you even remember the name quadratic formula, you've got a really good start. And everybody should be familiar with the quadratic formula. You might not remember it. Probably, the majority of the class will, a few people will. Maybe it surprised me and everybody knows it. I don't know. But you'll recognize that it's not difficult to learn to work with. And if you got this picture, it's not too difficult to see how it relates the formula for a function to these transformations of your basic x squared graph. Now, from here, we go on and we learn to make a good parabola. We learn to make graphs that have the shapes of what we call our toolkit functions. Our x squared function is one of our toolkits. We take this toolkit function and we can stretch it and we can move it around and we can get any parabola that we want, at least any parabola that opens vertically that we would like to have. And that gives us a very powerful tool for modeling things that are important in many fields of endeavor, including real life, including everyday life. So I'm going to build on what we've done here.